Today we're going to focus on model characterizations of feeds and rumen-protected amino acids. And what we're going to discover is that characterizations are all about rumen dynamics. And as we go through this, we'll develop these points and concepts more definitely as we go through her. Now we're just looking at generalizations. So characterizations are all about rumen dynamics, and we'll flesh that out as we go. And we're going to do that by asking a couple of questions. Number one, what are model characterizations? And why do they matter, or do they matter at all? So let's start with the first question. What are model characterizations? Because of this, because of the rumen, what goes in here is not what arrives here in terms of proteins and amino acids. Okay, so a few more points. Rumen dynamics. Rumen's basically a 50-gallon fermentation vat. And while in the rumen, microbial action on feeds alters their amino acid composition. We're talking about protein degradation in that rumen environment. And the susceptibility of feed protein to degradation while it's in the rumen environment is expressed as a percentage of protein degraded in 1 hour. So this is time associated. And we'll get into some of the details of this a little later in the presentation. So the extent of degradation of feed protein is determined by the time spent in the rumen and the rate of degradation. And rumen dwell time is determined by the rate of passage through the rumen. So this is time sensitive too. We've got a degradation rate per hour, and we've got a passage rate per hour. We're going to look at this from the perspective of Nrc 2001. The Nrc model characterizes protein in 3 different fractions, an A, B, and a C fraction. CNCPS does something very similar, only it has an A1, A2, and a B1, B2 fraction. Passage rates are calculated differently between the 2 models, and you don't always get the same values. In fact, you rarely get the same values comparing the same thing in both models. But what you will see here in general principles, in general terms, applies to both models. So let's take a look at Nrc approach here. Nrc uses 3 fractions, an A fraction, a B fraction, and a C fraction. The A fraction within the model paradigm is considered to be wholly degraded in the rumen. None of the proteins passes through the rumen and from this segment. The B fraction is considered to be partially degraded in the rumen. And the C fraction is considered to be wholly undegraded in the rumen. So that's our A, B, and C fraction. These are expressed as percentage of crude protein. And the A fraction plus the B fraction plus the C fraction equals 100% of crude protein. But there are some other factors here that are very important to understand. If I have a 10% A fraction, that's a linear value. It's going to remain constant all the way through the model's predictive process. So A fraction values are linear. They don't change. C fraction values are also linear, and they don't change. If we've got a 15% C fraction, all through the model predictive process, that's the value it will have. Not so with the B fraction. The degradation rates and the passage rates are only applied to the B fraction. They don't apply to the A fraction or the C fraction. Those are fixed values. They don't change. This one changes. RDP consists of the A fraction, what's wholly degraded in the rumen, and the degraded fraction or portion of the B fraction. RDP equals A plus the degraded portion of B. RUP equals the undegraded portion of the B fraction plus the C fraction. At all times within the NRC paradigm, RDP plus RUP equals crude protein. And these are expressed as percentages of crude protein. So the two together always equal 100% of crude protein. The B fraction is affected and is described within the model in terms of degradation rates and rates of passage. This is an important point because the passage rate is determined within the model by diet composition and level of dry matter intake, and these two are interactive. But the important point here is that passage rate is determined by diet composition. That means that RDP and RUP in any given feed are not fixed values. They are diet specific, not feed specific. And that means that from one diet to another, the RDP, RUP value of the feed will be different or can be different. If there's a B fraction, it will be different, and it will be dependent on passage rate and degradation rate. Degradation is a fixed rate per hour. Real variable here in all of this is passage rate. That's the unknown. That is only determined if we know diet composition and intake. So we're going to take a look at 3 feeds. These feeds are different in how they fractionate crude protein, and each one of them is a unique circumstance that we're going to look at. What you see on the screen is an ingredient profile record from Formulate 2 DFS. DFS is 100% NRC compliant. So what you're going to see here is exactly what you would see if you were using the evaluation software published with a model. So let's take a look at expeller soybean meal. Let's see how protein is characterized here. It has an A fraction, okay, which is right here, relatively small, 8.7%. It has a very large B fraction, and this tells us something immediately, because these two equal 100%, which means there is no C fraction. The A and the B fractions equal 100% of crude protein. So let's look at a couple of other things and we'll come back to this. The degradation rate is 2.4% per hour right here. And that's a fixed value that is not going to change through our illustration. Degradation rate is fixed, but passage rate is not. It's determined by diet composition and level of intake. So there's no value assigned here at the feed level, you see. This field is empty. In fact, within DFS will not let you enter a value here because it's all calculated by the model when evaluating a diet. Okay, RUP digestibility, 93% right here. That also is a fixed value. So what's not fixed here? The passage rate. The passage rate is not fixed. That means that the RUP and RDP values assigned to expeller meal by the NRC model is highly dependent on passage rate. Highly dependent on passage rate. almost entirely dependent on passage rate because there's only a small A fraction and no C fraction. So let's take a look at this. We're going to take expeller soybean meal. We're going to evaluate it. This is set up in DFS as a diet. It obviously isn't a diet because it's going to be 100% concentrates. But we're going to look at how the model describes RDP and RUP when we have an intake of expeller soybean meal of 1 pound versus an intake of 100 pounds. Now, when we're talking about a pound of soybean meal, expeller meal in a diet, we're talking about a pound of expeller meal as the diet. If we do it this way, that will generate some very different passage rates between 1 pound and 100 pounds. And that'll give us a very clear picture of the dynamics involved within the Nrc model in partitioning RDP and RUP. So we've got a diet with an intake of 1 pound as fed expeller meal. The model's going to generate a 1% per hour passage rate at this level of intake. Take a look at what happens to RDP and RUP at this very low passage rate. Nrc is modeling this as protein from expeller meal at this passage rate being 73% degraded in the rumen. 73%. Only 27% is partitioned as RUP. Now, that may seem surprising to you, but this is all due to the dynamic nature of degradation rate and passage rate within the model. So let's take a look at this same feed, but let's look at it at 100 pounds of intake, again, as a diet. The model generates a passage rate of over 9% per hour. So this passage rate is a little over 9 times what this is. Look what happens to RDP and RUP when we have an intake of 100 pounds as fed versus 1 pound. RDP is partitioned as 27%, not 73. RUP becomes 73, not 27. So these are just virtually reversed at the higher passage rate. And that means that any place in between, they will also be different. The only difference between these two evaluations is passage rate. The only difference. Okay, let's move on to canola meal. We're going to do the same thing with canola meal. First, we'll take a look at its profile. It has a much larger A fraction, which means it's going to have a smaller B fraction. But it's also got a C fraction. So that makes the B fraction even smaller. And all of this equals 100%. So different scenario. Expeller had no C fraction, canola does. So let's look at where it is. Degradation rate, much higher. Rather than 2.4%, we're looking at 10.4%, and roughly 4 or 5 times a faster rate of degradation. Again, with this feed, rate of passage is going to be determined and applied with degradation rates to the B fraction because it has a B fraction. So no value is assigned here. This is all diet determined. The RUP digestibility is a fixed value at 75%. So what is this telling us? It tells us that in terms of generating RDP and RUP values, canola meal is less dependent on passage rate with respect to the B fraction because it's much smaller. However, because the degradation rate is higher, time in the rumen becomes even more critical to this process of determining RDP and RUP. Let's do the same thing, run through the same scenario with canola meal. A 1 pound diet, all canola meal, same passage rate, 0.99%. Look at RDP, 88%, RUP 12%. Again, let's go back to canola meal at a higher rate of intake, higher passage rate. 100 pounds, 9.34% per hour. RDP, instead of 88, it comes down to 60%. RUP goes from 12% to 40%. And again, in this illustration, the only difference between these two evaluations is passage rate. So passage rate is a significant factor in determining RDP and RUP. Let's move on to a protected amino acid. This is Agipro-L. We're going to go through the same thing with Agipro-L. Agipro-L is set up with an A fraction of 19.5% crude protein. But look at this. There's no B fraction, 0 B fraction. That tells us right away that the balance of the protein is considered to pass through the rumen without degradation, and that's 80.5%, and there's our 100% of crude protein. So let's look a little at the details. It has a KD of 0. There's no degradation rate involved in this characterization. Why? Because there's no B fraction. And that's the same reason that there's not a passage value generated by the model, because KD and KP are not applicable to the A and C fractions. The RUP digestibility is 90.5, and that's a fixed value. It's not going to change. Okay, the A fraction, the C fraction, the degradation rate, and the RUP digestibility are going to be fixed, as it has been in the last two that we looked at. So let's go ahead with that same exercise with Agipro-L. And what we're going to find is not having a B fraction makes a big difference when you look at characterizations at different levels of intake. So let's go look at that. Again, same thing, Agipro-L, 1 pound intake, passage rate's the same. Look what we come up with RDP and RUP. And why is it the same? Because there's no B fraction. Remember, RDP is all of the A fraction plus the degraded portion of the B fraction. There's no B fraction. RUP is the undegraded B fraction plus the C fraction. There's no B fraction. So A and C remain constant. And you'll find the same thing over here. If we plug it in at 100 pounds and a passage rate of 9%, RDP and RUP are going to be constant at any passage rate. Now, as long as this characterization is truly representative of what arrives at the intestine, it's exactly what we're looking for. There's no B fraction, so passage rate and degradation rate don't have anything to do with this characterization at all. They only apply to the B fraction, if there is one. So, model characterizations, what are they? Let's kind of sum this up. Model characterizations attempt to describe and identify portions of crude protein that are wholly degraded in the rumen. That's the A fraction in the Nrc paradigm. The portion that is completely unaffected by the rumen environment, that's the C fraction. And that portion of crude protein, it is subject to rumen degradation over time. So what characterizations are doing is they're partitioning crude protein to RDP and RUP based on all of the things we've discussed. And a seminal part of that process is determining passage rate. And that's strictly for one purpose, to determine the extent of B fraction degradation. So determining passage rate is diet dependent. It's not feed dependent. RDP values for individual feeds are not assigned at the feed level. The model does assign RDP and RUP values to feeds, but that's only done within the context of a complete diet after diet passage rate values have been determined from diet composition and level of dry matter intake. So, are they important? Do they matter? Are characterizations of any significance? Yes. Because of the rumen, what goes in here isn't what arrives here. And let's look at it a little differently on a more specific level. Model characterizations of crude protein are critical. They're absolutely critical because in order to obtain optimal results from balancing diets for amino acid content, that can only be done when the predicted flows of essential amino acids have a tight correlation to the actual amino acid flows at the intestine. In other words, they have to be very reflective of what actually ends up at the intestine in terms of essential amino acids. Model characterizations of crude protein are absolutely essential to achieving that kind of tight correlation. It's not possible to achieve it without that. That's all we have for today. We thank you for visiting with us for a few minutes. In the next presentation, which has to do with predicted amino acid levels and actual amino acid levels, we're going to take a little time and explore some more on this idea of characterizations and why it's so important. And we'll take a look at a couple of examples of characterizations that are really problematic. So thank you for your time, and we'll see you next time.